This lecture will discuss rates of return, and the material comes primarily from sections 5.1 and 5.4 of Bodie, Kane, and Marcus. Let's begin by discussing what a holding period return is. Suppose we have a stock at the beginning of some time period that has price P sub 0, and at the ending of that time period, whatever interval of time that is, its price is P sub 1, and that at the end of that time period as well, it pays a dividend of D. Then the holding period return is the price at the end of the period minus the beginning period price plus the dividend all over the original beginning period price. This can further be decomposed as the capital gains yield, which is just the end of period price minus the beginning period price over the beginning period price, and the dividend yield, which is the dividend over the original price. This definition of holding period return isn't exclusive only to stocks, but can be used for other assets, such as a bond with a coupon payment instead of a dividend rate here. So let's take an example. On November 9th, 2012, Apple stock closed at $547.06. On November 12th, Apple paid a dividend of $2.65 per share, and the price closed on that same day at $542.83. So what was the holding period return? Using our previous definition, we say the holding period return is equal to the capital gains minus 547.06 plus the dividend, which is $2.65. And all of that is over P naught, where we can divide each part by P naught, so that we have the capital gains yield and the dividend yield. Interestingly, you'll notice that the capital gains is actually a loss. And it looks like I accidentally switched numbers here. That's a 547 instead of a 574. So what is the holding period return? Well, if you punch this into a calculator, you see that the capital gains loss is $4.23 on the original investment of 547.06, and you're adding to that the dividend on the original investment. And the total, if you punch this into a calculator, is negative 0.00289 rounding, which is negative 0.289% multiplying by 100. Now let's forget dividends and cash payouts for a moment. Then the capital gains yield we can actually write by decomposing the first portion as P1 over P naught and subtract off the second part of that fraction, which is just P naught over P naught, which is 1. Now this first portion, the capital gains yield, we refer to as a net return, whereas on the right hand side of the equation, what we have in the first term is the gross return minus 1. So what's the difference between net and gross returns? The net return is the fraction of your invested money that you gain by holding the asset excluding, and now that's the operative word, excluding the original money that you invested. So essentially what the net return gives you is for each dollar invested, how much additional purchasing power you have, not including the original purchasing power you started with. The gross return, on the other hand, it gives you the total gain, including your original money. So it gives you your total purchasing power at the end. So if you started with $1 of purchasing power, it will give you the $1 of purchasing power that you had at the beginning plus the additional amount, all wrapped into one number. So the gross return is also the factor by which you can multiply your original invested amount to determine the final invested amount. So let's suppose now that we want to consider multi-period returns. In the previous slides we were looking at returns over one period of time. So now let's say you have a sequence of returns from some time that we initialize at time 0 up to some time cap t. This could be any number of periods. Let's consider two forms of average returns. The first is just the arithmetic average. That is, these being net returns, we just take the sum of the net returns here and divide by the total number of observations. The second is the geometric average of the returns. So now we take the gross returns and multiply them so that we're compounding the returns over the whole time in which we're receiving the returns, over all periods. So this is the notation for taking the product over t intervals of time. And then to finish off the geometric average, you take the tth root because you've multiplied t things together. The geometric average, well, what is that? It's the constant return that would have to be earned each period to yield the same final value of the asset, which returns r sub t, which potentially differ each time period. To be more explicit about a geometric average, let's just think of t equals 2. So we have only two time periods. And in the first period, the asset pays R1. In the second period, it has a net return of R2. Well, then if I invest $1 into this asset, after time period 1, I should have 1 plus R1. So I have $1 times 1 plus R1. And that's the amount of money I have at the end of time period 1. And if I take all of those proceeds, meaning my original dollar, plus the amount that I earned, and invest it and keep it invested in the asset, then after time period 2, I should have this much money. Well, that's the total amount of money I have. The gross return over the two time periods being the compound return, 1 plus R1 times 1 plus R2. Well, what I can do is I can compute what would be the interest rate, R sub g, that would be constant over the two time periods. That is, not differing, whereas R1 and R2 potentially differ. Let's find the one single interest rate that I could earn at time period 1 and time period 2. And in so doing, I have to square this because I take my $1 and I increase it by 1 plus rg in the first period, and then again times 1 plus rg, and that's where the squared comes in. To solve for that interest rate that would yield the same final invested amount by compounding R1 and R2, what I have to do is actually take the square root of the left-hand side, or in the notation of the previous slide, I can eliminate this and do 1 over 2. So that if I write this a little bit more cleanly, what this implies is that the geometric average is equal to 1 plus R1 times 1 plus R2, all raised to the 1/2. And you could see how I could extend this to many periods, where if I had 3 periods, R1, R2, and R3, the equation I would be setting equal is 1 plus R1, the gross return, 1 plus R2, 1 plus R3. That would be the total amount of money I would have at the end of period 3 if I invested $1. Well, what would be the constant rate of return that would accumulate over which accumulated over 3 periods would equal the product of those 3 returns? Well, it would just be the right-hand side raised to the 1/3. And so then you can begin to see if I have t time periods, I would multiply the t gross returns and then raise to the 1 over t power to get r sub g, or 1 plus r sub g. Now let's talk about annualized returns. So suppose you enter into a contract to pay or receive, either way, a net rate of return r on an asset for each of n periods in a year. So now if n is equal to 12, that means you have a monthly contract. If n is equal to 4, you have a quarterly contract because you are going to pay or receive that rate of return 4 times a year. If n is equal to 2, you have a semi-annual contract. Then let's define the effective annual rate, or the EAR, as the value that would arise if you earned that one rate of return each of the n periods. So here you see, just as in the previous slide in the example, that you're taking the period return r, compounding it n times as a gross return, and you're getting what would be the annual return on the left-hand side. In a similar way, for the same contract, we can define the annual percentage rate, or the APR, as simply n times the period interest rate r. Now notice that the APR, it ignores compounding, as we'll see in the following example. Let's say that you have an asset that promises to pay a 5% return for each quarter over the next year, and that you have $100 that you'd like to invest in that asset. Then, after 1 quarter, starting with $100, you would have $105. And reinvesting the 100 and the 5 for an additional quarter, after 6 months, after half a year, you would have $110.25. And investing that, the original 100 and the earnings that you've gotten for the first half year, for 1 more quarter, you would end up with $115.76. And then once again, investing all that money for the last quarter, you would finally end up with $121.55. Now, if you computed the APR, what would that be? The APR says that you just take the net rate of return each quarter and multiply by the number of quarters that you receive it, which in this case is 4. So I would say I got 5% the first quarter, 5 the second, 5 the third, and 5 the fourth, for a total of 0.2 or 20% gain. But what was my real return on that investment? My real return, if I compute the holding period return over the year, the holding period return is actually equal to, what was it, 121.55 minus the additional outlay of $100 all over $100. So I really earned 0.2155, or 21.55%. What's going on with the APR? Well, it's negating the fact that not only after time period 1 am I reinvesting the $100. So after quarter 1, I'm not only reinvesting the $100 and getting $5, but I'm reinvesting the $5 gain after quarter 1, and after 2 quarters I'm getting an additional 25 cents. That is a 5% gain on the 5. So that's compounding working for me. And then after quarter 3, not only am I earning 5% on the 100, but I'm earning 5% on the $10.25, which gives me a total of not just $115 gained, but 115.76. And the same, again, I've compounded the extra 76 cents, and I have, in the end, an extra $1.55 over the non-compounded gains. So now let's consider what the relationship is between the effective annual rate and the annual percentage rate. Remember that the period return, little r, is the APR over the number of time periods. All I did was manipulate the equation that says APR is equal to n times r, right? What that means is that r is equal to APR over n. Well, in that case, because the year is equal to 1 plus the period interest rate raised to the nth power, we can relate the year to the APR by substituting this equation for the period interest rate. This means that we can also solve for the APR in terms of the year. In the first equation here, we have the year in terms of the APR. That is, if we subtract a 1 from both sides, we've solved for the year in terms of the APR. But if we manipulate the equation, it's pretty easy to show that, again, adding the 1, taking the nth 1 over n power here, subtracting a 1 from this side, and then multiplying that whole result there by little n, you get this equation right here. Continuous compounding, this is the case when we allow the number of time periods in the year, that is, that number n, to become very large. So if we're computing daily returns, then n is equal to 365. For hourly returns, 365 times 24 is 8,760. For returns each minute, how many minutes are there in a year? Well, there are 525,000. And if you wanted to compute returns for each second, you'll find that there are 31,536 seconds in a year. So continuous compounding is the limit as n, the number of time periods that we consider in a year for compounding, goes to infinity. In this case, we have this equation for the year, 1 plus APR over n raised to the nth power. As we take n to the limit, it turns out that this is the exact equation for Euler's number, E, raised to whatever value you have right here. That is, quite generally, if you remember from calculus, 1 over x, 1 plus x over n raised to the nth power, taking the limit of that as x goes to infinity, that is actually the definition of e to the x. And so what we have in this equation is e to the APR, because APR is now x. So using our previous relationship, we know that the year is equal to this side under the limit. And so under continuous compounding, 1 plus year is equal to e to the APR. Or if we reverse the mathematical operation, we can say the APR is the natural log of 1 plus the year. One thing to keep in mind as you look at these computations is that as you subdivide the year into more and more intervals, you are taking the annual percentage rate and dividing it into smaller and smaller amounts. So let's say that you have a 20% annual percentage rate, if you want to do semi-annual compounding, you would take the 20% and say each 6 months I will earn 10%, and then I will compound those together by 1 plus 0.1, 1 plus 0.1 times 1 plus 0.1. That's what the n is doing. It's effectively squaring this, which is what this operation is doing right here. And that will give you the effective annual rate. But if I want to compound hourly, well, as shown in the previous slide, there are 8,760 hours in a year. And so I would take that 20% and I would divide by 8,760, which is quite a small number. In fact, that number is 2.28 times 10 to the negative fifth, which is a very small return, but you're earning that return hourly, and you're earning it over the course of the year 8,760 times. So while you're compounding many more times, you're getting a much smaller return each period. Or alternatively, while you're getting a smaller return each period, you're compounding that many, many more times. Let's finish our discussion of interest rates by talking about nominal versus real interest rates and how they relate through inflation. Inflation is the increase of the general price level over time. So inflation erodes the purchasing power of a given amount of money that you have in your wallet over time. So in the presence of inflation, an asset that yields an interest rate or a return of R, a period return of R, doesn't actually generate R units of, and this is the operative word, real purchasing power for each dollar invested. What it gives you is R units of nominal purchasing power. But some of that purchasing power is washed away by the general increase in prices by the end of the time period in which you receive your return. So in the previous slides, we were computing nominal returns. And so I'm going to switch notation momentarily, and I'm going to call nominal returns capital R. So those previous returns that I was referring to as little r, we could call them now capital R, so that we know that they're nominal. Well, the real return of an asset is the nominal return discounted by inflation. So I take the gross interest rate, the gross nominal rate, and I divide by the gross inflation rate, where pi is the net inflation rate. Pi is something like 2%, or numerically 0.02. So this process of discounting is a way by which I deflate. I take what would $1 be at the end of a time period. Well, it would be invested, it would be 1 plus whatever the nominal rate is. Let's say that nominal rate is 0.1. Then I would have $1.10 at the end of the year, if my time period were a year. But let's say that inflation, all prices increased by 2% over the year. Then I don't really have 10 extra cents for every dollar, but I need to discount each $1.10 by 1.02, since I lost 2% of the value of each dollar earned. And the result then is the left-hand side, which is the gross real rate of return, where R is the net real rate of return. This relationship is approximated more easily by the net real rate of return being approximately equal, that's what these wavy equals signify, approximately equal to the nominal interest rate, net rate, minus the net inflation rate. Let's prove this on the next slide. To complete the proof, we're going to rely on an approximation, and that is, for some small positive number, epsilon, let's call it, the natural logarithm of 1 plus epsilon is about equal to epsilon itself. You can go verify this in a calculator. So let me begin by writing the relation that I had on the previous slide. That is, the gross real return is equal to the gross nominal return all over the gross inflation. And now basic algebra says I can take the natural log of both sides, and that should be equal to the natural log of 1 plus r all over this, where I'm taking the natural log of the whole fraction. Well, the properties of the natural logs dictate, first I'm going to leave the left-hand side exactly the same. It turns out the log of a over b is equal to the log of a minus the log of b. So let's take the log of 1 plus nominal rate minus the log of 1 plus inflation. And now using the approximation above, I see that this is r is about equal to capital R minus pi. Similarly, we can rearrange the equation and say the nominal interest rate is about equal to the real interest rate plus inflation. So if I'm earning a 10% nominal return and inflation is 2%, then my real purchasing power is about 8%. Here's a quick example from the book. Let's suppose that you want to invest in a 1-year CD and that it promises an 8% return. 8% nominal return. And that you expect inflation to be about 5%. Then what is the real rate of return? Well, you would say capital R is equal to, that is, let's rewrite it, capital R is equal to 0.08, pi is equal to 0.05, so that would mean little r is about equal to 0.08 minus 0.05, which is equal to 0.03, or that's 3%. Now, the actual real rate of return would be 1.08. All, that is, we should say 1 plus r is equal to 1.08 over 1.05. And it turns out that's equal to, 1.0286. So if I solve for the net interest rate by subtracting 1 from both sides, I get 0.0286 or 2.86%. You see that there's a difference. The true value of the real net interest rate is 2.86%. The approximated value is a little bit off. Now in practice, future inflation is not known, and so even though the nominal rate of return may be known with certainty, in the case of a fixed income asset, for example, we may not know what the real rate will be because of the unknown inflation. In this case, the proper relationship is that the nominal rate of return is equal to the unknown real rate plus expected inflation. Or we can rewrite in terms of our knowns. The unknown real interest rate is the known nominal rate minus expected inflation. Now if you take a typical government bond from the U.S. Treasury, the return on that is a nominal return. However, in 1997, the U.S. Treasury introduced what are known as Treasury Inflation Protected Securities, or TIPS. And these securities have coupon and principal payments that are corrected over time for observed inflation. And so the return on those assets should, in some sense, incorporate expected inflation, because the return on those should be real returns, taking the difference between the typical government bonds, which have nominal returns, and the TIPS, which have real returns. You should be able to back out what the market expectations are for inflation.